Have you ever just looked around and wondered what stops everything from just flying apart? I mean, from the phone in your hand to the very air you're breathing, our entire world is held together by these invisible forces. And today, we're going to pull back the curtain on those forces. Chemical bonds. Seriously, think about it. Why doesn't the world just dissolve into a giant cloud of individual, lonely atoms? The salt on your table, the water you drink, it's all just atoms connected to other atoms. The forces holding them together are what we call chemical bonds, and that's exactly what we're breaking down today.
So here's our game plan. We're going to start with the why. The fundamental reason atoms bother to bond at all. Then we'll get into the rules they follow and explore their two main strategies, either transferring electrons or sharing them. And finally, we'll see how these basic ideas create the three main types of bonds that literally build our world.
Okay, so what makes an atom want to bond in the first place? It really all comes down to the same reason a ball rolls downhill. It's a quest for stability. You see, a lot of unbonded atoms are kind of like a ball balanced right at the top of a hill. They've got a lot of potential energy, and they're just not stable. Bonding is how they get to roll down to a more relaxed, lower energy state.
And in the world of elements, who's at the bottom of that hill? The noble gases. Think neon, argon, all the way on the far right of the periodic table. They are the absolute peak of stability. They're the cool kids who don't need to talk to anyone because their outermost electron shells are completely full. They're perfectly content. And that is the dream for pretty much every other atom out there, to get an electron set up just like a noble gas.
So, to achieve that glorious noble gas stability, atoms have to follow a few key rules. You can think of it like a game, where every single player is trying to reach the exact same goal. And what we're about to cover are the fundamental guidelines they all have to play by.
And here it is. The main rule of the game is called the octet rule. For most of the elements we care about, stability means having 8 electrons in their outermost or valence shell. Burn this into your brain, because almost all the bonding we're about to see is just atoms doing whatever it takes to get to that magic number, 8.
Now, to help us keep track of all this, a chemist named G.N. Lewis came up with this brilliantly simple notation. A Lewis symbol just shows the element symbol, and you put dots around it for each of its valence electrons. It's fantastic, which you can see an atom's situation at a glance. Look at sodium. It's got 1 lonely dot it's looking to get rid of. And chlorine? It has 7. It is so close to having a full octet.
So how do these atoms get to 8? Well, the first major strategy is pretty straightforward. Just take what you need or give away what you don't. This is the great electron transfer, and it leads to what we call ionic bonds.
And this slide really nails the two fundamental approaches. Over on the left, we have ionic bonding. This is a total transfer, a complete giveaway. One atom loses an electron, another one gains it. Done. On the right is covalent bonding, which we'll get to in a minute. That's more like a cooperation, a friendly sharing of electrons between two atoms.
Now, the classic poster child for ionic bonding is making plain old table salt, sodium chloride. And if you actually take a chunk of pure sodium metal and drop it into a flask of chlorine gas, you get a seriously violent reaction. It gives off a ton of heat and light. It's what we call highly exothermic. But what is actually happening on the atomic scale to cause all this drama?
Well, down at the atomic level, it's a match made in heaven. Sodium, a metal, has what's called a low ionization energy, which is just a fancy way of saying it's really easy to pluck away its 1 valence electron. Chlorine, a nonmetal, has a high electron affinity. It really wants to gain an electron. So sodium is more than happy to donate its electron, and chlorine greedily snatches it up.
Okay, so after that transfer happens, we don't have neutral atoms anymore, right? The sodium, having lost an electron, is now a positive ion, Na+, and the chlorine, having gained one, is a negative ion, Cl-. And what do we know about opposites? They attract. These brand new ions are now held together by powerful electrostatic forces, and they arrange themselves into this beautiful, highly organized, and very, very stable 3D structure that we call a crystal lattice.
And the super-rigid lattice structure? It directly explains all the properties we see in the real world. Why do ionic compounds like salt have such high melting points? Because it takes a massive amount of energy to break that strong lattice apart. And why are they brittle? Well, if you hit a salt crystal and shift the layers just a little bit, you suddenly line up positive ions next to positive ions, and they repel each other, shattering the whole thing.
Now, you might be thinking, wait a minute, didn't you say it costs energy to pull an electron off sodium?
And you'd be absolutely right. That part of the process actually requires an input of energy. But here's the secret. The real energy payoff comes at the very end. The formation of that stable crystal lattice releases a massive amount of energy, something we call lattice energy. And this huge release of energy is what makes the whole process worth it, making it favorable and exothermic overall.
Okay, but what happens when you have two atoms that both want to gain electrons, like two nonmetals? An outright transfer just isn't going to work. This brings us to our second major strategy, the art of sharing electrons, which is what forms covalent bonds. Yeah, when two atoms have a pretty similar desire for electrons, neither one is strong enough to just rip an electron away from the other, so instead they come up with a cooperative solution. By sharing one or more pairs of electrons, both atoms get to count those shared electrons as part of their own octet. It's a win-win that allows both of them to reach that stable state.
And here are two perfect, simple examples. A hydrogen atom has one electron, but it wants two to be stable. So if two hydrogen atoms get together, they can each share their one electron, forming a single bond. Now both of them are happy. It's the same deal with chlorine. Each atom starts with 7 valence electrons. By sharing one pair between them, they each get to count 8 electrons in their outer shell. Boom, octet rule satisfied.
But is that sharing always perfectly equal? Not a chance. The concept that governs this is called electronegativity. You can basically think of it as a measure of an atom's greed for electrons when it's in a bond. Some atoms pull way, way harder on those shared electrons than others. So when two different atoms bond, the one with the higher electronegativity, the greedier one, is going to tug those shared electrons a little closer to itself. This creates what's called a polar covalent bond. You end up with a partial negative charge on the more electronegative atom and a partial positive charge on the other. It's still a sharing-based bond, but it's an unequal, lopsided sharing. It's more of a tug-of-war. All right, so we've covered the two major strategies that atoms use to find stability: transferring and sharing. Let's zoom out now and summarize the 3 fundamental ways that our world is actually held together.
This table sums it all up really nicely. First, you've got ionic bonds, which come from that electron transfer, and you typically see them between metals and nonmetals. Then you have covalent bonds, the result of sharing electrons, which happens between nonmetals. And then there's a third type, metallic bonds. In a pure metal, all the atoms are held together by this delocalized sea of electrons that just flows freely among all the metal ions. That's actually what gives metals their unique properties, like being able to conduct electricity.
You know, it's pretty incredible when you stop to think about it. These few simple principles, the relentless quest for a full octet, achieved through either giving up or sharing electrons, are responsible for the staggering complexity and diversity of literally all the matter around us. Which, it leaves us with a really fascinating final thought. These rules build our world, but what's often most interesting in chemistry is when the rules get broken. So what happens when atoms decide to do just that?